Okay, thank you for the opportunity. My name is Hanna. Zakiyya. I come from the Faculty of Material Science and Engineering of Miskolc University. Actually, this paper is quite a technical thing, so I hope this paper later will be one of the opportunity where the entrepreneurship can grow better. So the topic is spent picking liquor as a waste recovery opportunities. So our focus is recovery of pure zinc from hot dip galvanizing industry. So the background of this study is we have a large source of spent pickling liquor where all around Europe we have 300,000 meter cubic per year of spent pickling liquor came from the hot dip galvanizing industry. And what is spent pickling liquor actually? And this liquor came from the pickling bath where the hydrochloric acid was used to clean the surface of metals, to remove the metal rust, scaling, and also some unwanted coating or unwanted coating, especially zinc coating. So actually after certain cycle, this liquid contain a lot amount of metal, some amount of metal, rich of metal, especially zinc and iron. And of course, because it's have some amount zinc and iron, because it is a heavy metal, it's considered as hazardous liquid, and it has to be treated to meet the European regulations. And our concern is to transform this kind of waste into the valuable resource, and we are focused to make it a high purity, even in zinc or iron. But in this experiment, we will focus on zinc. Well, previously we did it with iron, and we got pure iron as the result. But then we still have zinc as a remaining liquid. So why don't we did it with zinc as well? So why high purity is important? Because high purity will increase its value of the metals. So here we know that this is the example when we have 5N zinc, or we can see like 99.999 zinc, it will increase the price of this zinc by 4,000 times compared to the common zinc. And this kind of zinc can be used in as the raw material in the semiconductor and medical, or in the radiation detector, infrared substrate. Is there any technology that's been used in the industry to solve this problem? Yes, it is. There's some like neutralizations. This is the widely used in the industry, where the neutralization and precipitations actually only reduce the volume of the waste, but it's not even get anything from the waste. So in the neutralization and precipitations, we still have that waste in the kind of sludge at the end. But then we have spray roasting. And the spray roasting, there's two methods in the spray roasting. Actually, there's a spray roasting where we use the waste of heat from other plant. So we use the 450 degrees Celsius to make the hydrochloric acid regenerate. Yes, this is good. We can fully recover all the hydrochloric acid, but not with the metals. And then they also have like a fluidized bed spray roasting type, but it will consume more energy here because they need 650 degrees Celsius. But then there's also solvent extractions. In the solvent extractions, actually, it's quite good because here we can also get the hydrochloric acid and also the metals as the salt. So the salt, the zinc chloride or the iron chloride can be used as fertilizer. But the investment for this equipment is quite high. And then in some literature, we have also ion exchange and membrane separations, but still this process has to combine with the other process that we want to do now. And still the result of this process has not meet the yield acceptance product, especially if there is zinc and iron is combined or coexist in the liquid. So the current background of this paper is actually we did some electrodepositions from zinc from the SPL to recover zinc. Yes, we know that electrodeposition was widely used to recover zinc from any solutions in the world. So 80% of the zinc productions come from the electrodeposition side. So why don't we use it for the SPL as well? But still there's a lot of problem, as we know that the zinc has the far over potential to the hydrogen. So the problem will be always hydrogen reductions accompanying the main reactions that we want. But then with the including or with the existence of iron, these conditions even worse, because the iron with the lower over potential to the hydrogen evolution to hydrogens, so it promote the hydrogen evolutions where it will decrease our efficiency. In other way, this iron also co-deposit with our zinc. So this is our problem. So we want to combine the electrodeposition things with the available technology that has been used in the industry to recover these SPL things. This is the aqueous purification. Here we use, there are two actually, there's hydrolytic precipitations and anion exchange. And in this paper, we will focus on the anion exchange. So in the previous result, we know that the pattern growth of the depositions of zinc from the SPL, it's as usual in other zinc depositions, it starts with a dense zinc, and then it's spongy, and then start dendritic. This spongy is a proof that the hydrogen evolution is there, but then the hydrogen evolution is worsened to make some dendritic pattern here, and also this is because there's decreasing in zinc availability near the surface. And then what happens if the iron is there? When the iron is there, the pattern is still the same, but here we can see that there's some decrease of the dendrites. So our resulting metals or deposit is actually good as a visual things. But if we look at closer to this, we can see that the porous surface is happened there. This is can we say here the hydrogen evolution is not only give us the drawback, but sometimes it's give us the benefit, because it's make a turbulence where we make the compositions in the solutions is uniform. But then let's see what about the compositions obtained after in the potentiodynamic runs with some compositions of iron. Here, the bar one is for the iron and the line is for the zinc. Here we can see that if we don't separate the zinc and iron, even in small amount of iron here, we still see that iron will contaminate our result. And as well as is this increase, the more iron is deposited. But what is interesting here, we can see here at the compositions of iron like 45 to 60, it's increased it's promote more zinc depositions while more iron is inside the solutions. So if our goal is co-deposition things, this condition is good to be done. But if because our goal is in the purity case, so we need to remove the iron before the electro deposition stage. And here the result of the current pattern when we do the electro deposition. Here we can see that to get this current, or it actually represents to get a deposit, or another reactions, the reduction here, a reduction reaction here. This one is the highest one. This is free of iron, but actually here still there's some hydrogen evolutions. Here we can see the current here is 1.5, and There's what we can see here, if we put some iron, so the process getting slower, and even the gaining to gain the the same amount of current, we need more time, and even we need more potential, which is not good for the process, because it's will consume more energy here. And so that's why we need to introduce the purifications. Here we can use the hydrolytic precipitations and anion exchange, because theoretically, here we can see the hydrolytic precipitations in this range of pH. We can separate the zinc here and the iron here. So we can put some maybe the sodium hydroxide to the solutions to make it to precipitate the trivalent iron here. But then let's see the change with the anion exchange. In the anion exchange, but here, what is the drawback of this process? The trivalent iron will lose because of the precipitations. We will have it as the precipitate. But in anion exchange, we can get it both in the liquid stage, so we can electrodeposit either zinc or iron here. Here we can see the anion exchange distribution functions from the iron and zinc. The separate lane here can be drawn here. If we have the trivalent iron in the solutions, it's better to do it before 1 pH. But if we have divalent, so we can wider this range to 2.5, and it's better to do it in divalent iron, so we can have a wider range of work here. And it can be done by reducing the iron trivalent to iron divalent. And this is the principle of the ion exchange chromatography, by the way. So this actually we use the immobilized phase. Here we use the quaternary amine, and which is we equilibrated with the hydrochloric acid, where the chlorine ion is used as the radical who will make a complexation with the zinc, and then the iron, it will go through the column. And this is the process where we use the rinsing, elutions, and another elutions to make sure that all the iron is out from the column before we want to take out the zinc to separate it. And then from, okay, this is, sorry. So here we can see that the iron can be separated from the zinc. So actually, if we can see here, we have the column when we put the same solution inside it. So the zinc will retain with a bit of some resin here, and the iron will go out from this system, And this one, at first, they will go out from this system because it's not reacted with the resin bed in that range of pH. And then after that, because we want to get the zinc as the solutions, we can also remove the zinc with a little amount of hydrochloric acid and sodium hydroxide. Then we will get the solutions of the zinc, pure zinc. Because here we can see there's no more iron is here. Iron is already out, all of iron out, get rid from the solution already in the first stage. And then we can continue it with the electrodeposition stage. So the economic benefit actually for this process is, if we have 300,000 meter cubic of discarded pickling liquor all around Europe, which leading to costly and energy intensive handling, treatment, and disposal. This technology will offer us the domestic energy saving, because we will cut some process which consume a lot of energy, and of course, we also cut the energy transport. As well, we also cut the CO2 cost. And annual cost saving because of neutralization has needs some landfill place. It can be avoided, and it's also eliminate the need of neutralized pickling waste, where it's significant for the environmental. And raw material can send back. The raw material of hydrochloric acid can send back to the pickling bath, and it's make an opportunity where the entrepreneurship can grow. And the finding is the recovery of pure metal from the SPL is possible by conducting the electrodeposition process, and it will be better if we do it. We do the separation process before, so we can do it with the anion exchange process. And yes, it will solve the problem like waste disposal, resulting in significant saving in operating, environmental, and capital expenditure. And also we have the high value product is the high purity zinc. Okay, so this all the end of my presentations. Any question and comment are welcome. Thank you.